Hello there, Mr. Vessel here again, and we are looking at another bivariate data question from an AP Statistics exam. Today we're going to look at the 2011 number 5 problem, and this one is going to have us look at one of those computer output questions and have a couple of different uses for reading that table there. So let's dive in and check out this problem. So thing you'll notice, this one is got a little more, like a lot of AP questions. It's got a lot of text to sift through from the beginning here. So windmills generate electricity by transferring energy from wind to a turbine. A study was conducted to examine the relationship between wind velocity in miles per hour and electricity production in amps for one particular windmill. For the windmill, measurements were taken on 25 randomly selected days. When the computer output for the regression analysis for predicting electricity production based on wind velocity is given below, the regression model assumptions were checked and determined to be reasonable over the interval of wind speed represented in the data, which were from 10 miles per hour to 40 miles per hour. And the printout's right in front of us. And again, these printouts have a lot of similarities from printout to printout. Now, they're not all identical. But we'll come back to some of this. The big thing to notice here is you'll see one of the predictors in this case is wind velocity. This is going to be our x variable. And we have the one for the constant. And the first task actually asks us to use the computer output to determine the equation for the least squares regression line and identify all variables used in this equation. And we're going to find the two key numbers for answering this question are going to be the first two under the coefficient spot here. This one, the top one, is the y-intercept. So we'll need this number to make our equation, and we're also going to need this one. This is our slope. And then we're just going to create this equation out of this. So now the spacing here is a little off and we flipping back and forth here. But for part A, we want to make an equation, and you can use x's and y's in this case to make equations. I find it often helpful to not use x and y, but rather just describe the variable. And in this case, what we're trying to make an equation for was electricity production. So that's going to be our y variable. So you can use y, and you have to remember it says to identify the variables. So if we use x's and y's, we just got to label them. I'm going to use just a more direct approach here. I'm just going to use electricity production, and our equation predicts. So we're going to use a little hat. That's a really important part of making your least squares regression line. It's a prediction equation, and in this case it is the point 137 plus 0.240, and then the x variable here is wind velocity. Like I mentioned, you can use other descriptions if you want to use something like y hat or even e hat. If you want to say e hat is electricity production, or w here for wind velocity, that'd be okay. Just want to make sure that you identify those variables. If you actually just write them down, you've identified them, so you don't have to do that again. Sometimes it is helpful, like if you wanted to put the units on these, you can. This one's in amps, and this one was in miles per hour. So part A is really just reading that chart, knowing where to go to find your y-intercept and your slope. And then the next part looks at the equation. I guess there's a couple of ways to approach this one. It says how much more electricity would the windmill be expected to produce on a day when the wind velocity is 25 miles per hour than on a day when the wind is 15 miles per hour, and show how you arrived at your answer. I think there's two really good ways to go about this one. One way, I think this one's the one that comes maybe quickest to students. If it says how much more electricity would be produced when the wind velocity is 25 versus 15, a lot of times students will just take those two numbers, plug in the number 25, plug in the number 15, and just simply calculate it. That's a perfectly fine way to go. You can get your two responses. And what that would look like in this case, I'm going to try this for a second here. So let's say I wanted to do electricity for 25 miles per hour. And you can plug in the number 25, just see what you get. I've done that ahead of time. It turns out that you get 6.137 amps. And you can contrast that, do the same thing with 15. Electricity. Oops. For 15 miles per hour. And you plug that in as well. Same strategy. And that number comes out to be a little bit less, 3.737. And now that you have these two values, it's pretty quick to calculate a difference. So the difference between these two you can take the 6.137 minus the 3.737, and you'll find 2.4 amps is the amount that 25 days is more than on the 15 mile per hour wind day. So that's it for part B. But another really clever way to think this one through is actually you don't need to type in your equation here for 25 and 15 and subtract. You could actually just apply the concept of slope here, and I think that's a really great way to do this one as well. Maybe even be a little more efficient, is to notice that, well, if the slope is 0.24, I'm going to put another alternative method up here. So for part B, another alternative could be to just analyze the slope. Since the slope is 0.24, and what we remember about slope is it's the rate at which the, in this case, electricity production increases for every single mile per hour of wind. So if we know that the wind increases, from 15 to 25, that's a 10 mile per hour increase. That's a pretty simple calculation too. If I just use my slope, 0.24, and again this is amps per mile per hour, so it's got units on that, and then if I'm increasing by 10 miles per hour, we just end up calculating it directly, 2.4 amps, just by multiplying the 10 miles per hour times the 0.24 amps per mile per hour. So this is another way to think that through. Either one would be perfectly fine on the AP exam. Just sort of have some options sometimes, and a lot of times students like the direct method of plugging in the two values and subtracting to get the 2.4. This one, again, maybe a little bit quicker, but if that one doesn't come to your thought process, then that might not be the best method, where you can just use the slope and multiply by that increase in miles per hour. So they give you the same value, and definitely not both of those methods would be required, but just having one that you could use to show how you get your 2.4 is all you need. And part C, that one gets into, says what proportion of the variation in electricity production is explained by its linear relationship with wind velocity. We haven't gotten into a lot of this table actually. Many of these tables will have an r squared value. Sometimes they'll have an r value. Sometimes even have this r squared adjusted value. This one you'll never use, by the way. So the proportion of variability in a y variable that could be explained by an x is the definition of r squared. So really this one is just asking you to realize that this number, the 0.873, is the proportion of variation in electricity production that can be explained by its linear relationship with wind velocity. So it's really just noticing that this number is r squared, and that value is just given right in the chart. So a pretty straightforward task, as long as you can read the table, knowing that r squared is the proportion of variability that's explained by the x. So I like to think of it this way. Sometimes this is a confusing number for students. So this 87.3%, what that tells us is that the amount of electricity production, 87.3% of it can be explained by the wind velocity. And what that also tells me is there must be about a little 12.7% that's not explained by wind velocity. It might be some other variable out there that could determine how much electricity is produced other than wind. but 87.3% of the electricity production can be explained by that linear relationship with the wind velocity. So more wind is going to be more electricity production. So that's all there is for part C, is just recognizing that this 0.873 is what that proportion of variation is. And then the last task is getting into statistically convincing evidence that electricity production by the windmill is related to wind velocity. So I'm going to go back to this chart here a second. Basically, it's sort of looking at, doing an interpretation of a hypothesis test without actually going through and doing the whole hypothesis test. And while we haven't really mentioned some of these other numbers here, I'll do a rundown of some of these values here. So the standard error of the coefficient, the t value, and the p value, t statistic I should say, and p value are all on these charts here. And it's really, really rare, maybe I could say almost never, you will use the standard error for the constant and the t-score for the constant, because what this sort of shows is just, is the constant 0 or not. You usually don't care if the constant's 0, so you can ignore these numbers. The ones that do come in handy is the standard error, the coefficient, the t-score, and the p-value, but really you don't need all of them. The t-score, if you cared, is calculated just by taking the 0.24 divided by the standard error. This is your test statistic. This is your standard error of the coefficient. So when you divide those two, you'll get this t-score. And then when you look up this t-score, you get this p-value, so it's almost 0. And really with part D, I think choosing one of these two numbers to do your conclusion is really perfectly fine. I'm going to go with the p-value and interpret the p-value that way. One more number that I wanted to mention that we didn't talk about, this S over here. This one, again, it's not super common to get asked questions about it. What it is the standard deviations, or sorry, the standard deviation of the residuals. In this case, remember they said there was 25 randomly selected days. So they must have 25 data points, and these would be the standard deviation of those residuals, which is a pretty useful number. Remember, residuals will always add up to 0 if you total your residuals. So the mean of a residual set at data is 0. But the standard deviation can be really helpful. It's like an average away from the mean. So you can expect each day to be about 0.237 amps from the line, essentially, each data point. So that's what S represents. And again, we don't need it very often. We definitely don't need it in this task. All we really need to do for part D is interpret this p-value. So something, got a little space down here, says, is there evidence that there is convincing evidence? Let me go down here for part D here. So I think what is helpful to remember is that if we were to do a full hypothesis, the null hypothesis in this case would have been that the slope is 0. And then the alternative hypothesis would have been that it's non-zero. And that's true for all bivariate hypothesis tests for slope. You want to see if it's got a relationship or not. So if you assume there is no relationship, you start with 0. And what we found in this particular sample is that the p-value is almost 0. So we can say something like, since p, which equals 0, 0, 0, is less than pretty much any alpha level we would choose. Let's say we use 0.5. I'll just alpha 0.5. There would be significant evidence to reject the null. And I haven't put it back in context yet, so I do want to make sure that I say that there is convincing evidence that electric production is related to wind velocity. And that would wrap it up, just sort of knowing that it's couple pieces here that are really important. We would have had to know what the null would have been, but really the important link is just mentioning that our p-value is extremely significant compared to some alpha level. So that means that yes, there is a relationship between wind and electric production, and it's significant. So that would wrap up with part D and actually the whole number 5 from 2011. So I wanted to say thanks for listening in, and hopefully this is helpful information. Comment below if there are any questions or comments. Thank you.